Hello, YouTube! Today we're going to talk about how to do calculations with constant velocity. This is honestly not necessarily something that should be in Physics C, just because it kind of feels like a thing that you should hopefully be pretty comfortable with. But we're just going to explicitly state it out and have it anyway. So in particular, end of the thing, you should be able to model the motion of an object moving at a constant velocity and use calculations to do that. In particular, you should be good to go with figuring out what the givens are, using the correct equation, solving that equation algebraically, as well as solving a system of equations, and then using reference frame shifts to model what's going on there. So the equation we're going to be using for this is that your current position is equal to your initial position plus whatever velocity is in that direction times time. And this only works if you have a constant velocity. If you think back to the average velocity equation, this is very similar to the average velocity equation in that if you rearrange this, it's that delta x is equal to velocity times time. And this will always work either with constant velocity or with average velocity, because average velocity functions as though it is constant velocity. So that's a big part of why I want to talk about this one, even if it's maybe not necessarily as sort of difficult as this course can get. In particular, this is, I think, one of the first times we're seeing subscripts. So if you see a variable and then you see a little mini thing to the bottom right of the variable like this, what it's telling you is a modifier of the original variable. So this is current position. This is position at the beginning. Not is initial normally. This is a velocity. It's the velocity in the x direction. If this was y, it would be for the y direction instead. So using that to solve out an example, and we're going to come back to this a couple times, A will be just sort of doing it with what we just learned, and then B will be applying that to multiple objects. So you and a friend are driving to New York. You start out 30 miles behind your friend and 210 miles from New York. You drive 70 miles per hour. Your friend drives 60 miles per hour. And I might have made this problem so that you reach there at the same time as them, and I just realized that. But we'll see. So problem solving approaches. Oh, I do have to actually do it. All right. Actually, I should use a different sheet of paper so that I can scan it in. Stalling for time. Oh, that's got some gunk on it. Fascinating, I know. Okay. So we've got our friend, and we start out 30 miles behind our friend, and we are 210 miles from New York, which means our friend is going to be such that the distance that we are versus the distance they are needs to add up to 210, or 210 minus 30, which will give us 180. So A, how long does it take us to reach New York? So going through and identifying our givens, we're asked for the time. We have our initial position. You get to pick a place and call it 0. Let's just call where we start 0. Let's call New York all the way at the end of 210. So our initial position for this one is 0. Our final position for this one is 210 miles. And our velocity for us is, I'm going to just pop a Y on all of these to let us know that it's for you, is 70 miles per hour. So if we want to just go ahead and use the equation, we've got x equals x naught plus Vx times t. We're going to plug in our givens, as we know that we've got the final position of u. I know that this one is 0. I know that this one is the final position, the velocity of u times time. I plug in the 0 because it tends to make the algebra easier. Otherwise, I would say don't plug in numbers until the very end. It'll make sure that you're doing things correctly, and it'll also help you out if you have to do it again, because it'll just already be solved. At this point, we just need to divide by the velocity, and we're good to go. And so that'll give us that your position at the end divided by your velocity equals the time. Go ahead, plug in our numbers. We've got 210 divided by 70, and we're good to go. So 3 hours. And hopefully that was pretty straightforward. The way that can get a little more complicated is if we start to then have to solve for a system with 2 objects. And for that, all you basically want to do is set up the same equation once for each object, and then solve for one in terms of the other, plug it in, and you're all set. There's a quicker way to do it using relativity that has more conceptual difficulty associated with it, but can lead to less algebra. And we'll learn that one after. Oof, it is getting late. So here's our same setup, except for this time, instead of what we were trying to figure out last time, we're just going to go in and find what the time for, and this is specifically saying you are catching up with your friend. That means that the position of you needs to equal the position of your friend, so I'm just going to call them the final position. We know that the initial position for you is 0. We know that the initial position for your friend is 30. We know that the velocity for you is 70. We know that the velocity for your friend is 60. And so what we can do is, and time is our variable, is set up an equation for each of these. X is equal to xu naught plus the velocity of u times the time. And we're just taking our original equation up here and plugging in the specifics of this situation. And then we can do it again for your friend. We've got the final position will equal the initial position of your friend plus the velocity of your friend times time. Now, nicely enough, this one is already solved for, and I am going to go ahead and just save myself a little bit of effort later and plug in the 0. This one is already solved for position. So if I take this and I replace every time that position shows up in this equation with this equation, we'll have a situation like this where we've got the velocity of u times time equals the initial position of your friend plus the velocity of your friend times time. So now if we want to solve for time, first step is going to be to get everything with a time on it to the same side as each other. Just going to go ahead and bring that to the left via subtraction. That'll give us something like the velocity of u times time minus the velocity of your friend times time will equal the initial position of your friend. And then all we have to do is factor out. And when we do that, we'll get the velocity of u minus the velocity of your friend times time is equal to the initial position of your friend. Divide by the velocity of u minus the velocity of your friend. And we'll get that our time is equal to position of the friend divided by the velocity of u minus the velocity of the friend. If we had left in the initial position of u, it would have wound up such that this would be minus the initial position of u. And that would wind up being useful for something else when we're talking about relativity. We will wind up getting to the same place when we think about this with the relativity. But for now, we'll just call it like that. We've got 30 over 70 minus 60, which gives us 3 hours, which for C means that when you show up, your friend also shows up and you get there at the same time as each other because of your speed differential. All right. So really quickly talking about relativity and reference frame shifts is sort of a second way to solve problems like this. All motion will be relative to a reference frame. So another way that to say that is that like something has to be stationary, but we're on a planet that's moving around the sun incredibly quickly while rotating incredibly quickly while that spins in a galaxy moving incredibly quickly. And for all of these things, it's not that we can tell that that's happening. And the reason for that is because we're in a reference frame where, for us, that's what stationary looks like. You can do the same thing in a physics problem. You can change the way you're thinking about it. So instead of thinking about it from the perspective of someone standing on the sideline of the physics problem connected to the Earth, you can think about it from the perspective of one of the objects or something else that makes the math easier. And when you do that, one of the objects the one in the reference frame you're working around, will seem as though it's not moving, and everything else will be moving around it. One of the core tenets of physics is that laws or rules still have to work regardless of what reference frame you're in, and things have to work the same way between reference frames. So this is always a thing that you can just kind of do. So how to do it is the next thing we're going to talk about. In particular, we're going to derive how reference frames are going to be related to each other, and then you can use that concept to shift between them relatively easily. So the place that reference frames come from, and probably the easiest way to figure out a reference frame shift, is if you take two sets of axes. We're going to call this one A, and we're going to call this one B. So you basically have two different origins, and you could also have two different orientations. Those two different origins are a set distance away. And if we draw a position vector going from A to B, this will be our sort of reference frame shift to get from A to B. Now let's say that we've got a point, C. An interesting thing about C is that it exists just in space. B is shifted up and to the right from A. So if we're looking at this on a graph axis, it's a different combination of points from A as it is from B. From B, it looks something like this. But from A, it looks something like this. And what's neat about that is that you can use the basis of vector addition to add these vectors together and use that to give you a relationship. If you know how to get from A to B, and you add that to how to get from B to C, that will give you how to get from A to C. And if you want to flip the direction on this arrow, that'll be fine. You just have to add a minus sign. So what I like about this is that it's fairly easy to remember. If you remove the middle letter after adding them, you'll get the final shift. Now this isn't particularly useful because normally the shift you'll want is this one, or it's not particularly useful as is. So most of the time what you'll want to do is also subtract off AB. So if you want to find reference frame BC, as in you are in reference frame A, you know how to get between how to get from A to the point you care about, and you know how to get from A to B. If you make from A to B negative, and you add the other one, you'll get from B to C, Or alternately, if you're looking for how to get from A to B, you would subtract off BC. And you would have the first one minus the second one, and that would give you how to get from one reference frame to the other, just in general, as long as you had some third reference point. What's even more useful about this, and this is sort of a way that you can shift locational reference frames to be like, where does each person think this object is? And how can I translate between those? This is even more useful if you think about it in terms of time derivative, because if you take the time derivative of each of these, it still works. Because the time won't function differently between them, basically. So if we take the time derivative of this, then this also works for velocity. But because it also works for velocity and we can take the time derivative again, it also works for acceleration. So if you're trying to figure out the relationship between different reference frames and then use that to shift from one reference frame into another, this is how you would do it. And the reason you would want to do that shows up in the sort of New York example. If we take this 210-mile trip and we instead think of it using reference frames, what we can do is we can say the distance from you to your friend, which in this case would be AB, where you are A and your friend is B, will be equal to the distance from you to New York minus the distance from your friend to New York. And this is if we took this one and subtracted off BC. But that's also true for the velocities. The velocity of your friend is according to you. So the order here is the thing you're seeing according to the thing that's doing the seeing. So the velocity of the velocity that you see your friend going will be equal to the velocity that your friend sees New York going minus the velocity that you see New York going. And the reason that this is so useful is because we can take this and get sort of a composite velocity, because in your reference frame, you aren't moving. So if you think of this problem as your velocity with respect to you is 0, which means that when we go ahead and do our equation, the equation for you is going to look like your position is 0 at the beginning, your velocity is 0, so just it's the origin. But when you look at the equation for your friend, the position of your friend will be this. We need to take the position of your friend and figure out where your friend is as compared to you. Well, your friend as compared to you is 30 meters in front of you. So the final position of your friend is 0 because they wind up on the origin where you are. And your initial position of your friend is plus 30. Additionally, we can take the velocity that you each see each other going to get the velocity that you see your friend going. Your friend sees point C from New York. I did this backwards. This should be the velocity of you compared minus the velocity of the friend. Nope, I did it right the first time. Sorry about that. So the velocity of your friend is that 60. the velocity of u is that 70. And so when you subtract them, you see your friend as going at negative 10 meters per second, or miles per hour, which we can plug in over here. And the reason that's so nice is now we don't have to do a system of equations, because one of our equations, everything just equals 0, and our other equation, we've got it all set up. That'll give us that once we solve this out, which we can do by subtracting off x f naught, subtracting off x f naught, that'll give us xf minus xf naught equals vyf times t. I'm resorting to old habits on my t's. Divide each side by vyf, divide each side by vyf, which, remember, the way that we got that was by subtracting the two velocities. And subtracting the two velocities with the opposite sign as the way we're subtracting the two positions. So we'll get position of your friend minus the position of your friend at the beginning, as according to you, divided by the velocity of your friend as according to you. And that'll equal your time, which will give us 0 minus 30 over negative 10, or 3 hours. So we get to the same place, but we don't technically have to do as much of work with the system of equations if we're able to think about what it looks like is happening from our perspective and use that. And this is just sort of a formalized way to make sure you're doing it correctly. But if you're comfortable just thinking about it and using that, that should work as well. All right, sorry for all the mess at the end. Hopefully that wasn't too bad. Goodbye, YouTube.